Good morning, everybody. Today is Codeforces Global Round 12, so it's a big round. It's Div 1 and Div 2 combined, so even if you're in Div 2, you'll be competing against me. If you beat me, your elo will go up, assuming I don't do absolutely terribly. And it starts in 6 seconds, so good luck, have fun. We've got a new template, and I'll see you on the scoreboard. There's going to be less commentary than usual today, because it's rated for me, so I'll be focusing on the contest and doing a lot of my work on paper. Subsequence of A if B can be obtained by A by deleting some characters. Given some string, you want to reorder the characters of A so that try grub is not a subsequence. This is not sorted, so we can sort it. We have a marvelous proof. Thank you. Very good. I like it. Yeah, okay. Sort A. Yeah, okay. Run samples just to be sure. That's right. Goal today is to read all of the problems that get solved. Got it, nice. And distinct points and a non-negative integer parameter k. Each point is a microscopic steel ball and they attract power when it's charged. Okay. On operation, you can select a ball I and charge it. Once charged, all balls with Manhattan distance k from ball I move to the position of ball I. So it's always either -1 or 1 or 0. All points are distinct, so -1 or 1. Yeah. Very good. Oh, sorry. Oops, my bad. Okay, so we've got this, and then we want to check each ball. So then if f.abs of x is at I minus y is at, or minus x is at j, plus math.abs of x is at, or y is I minus y is j is greater than k, and same with the outer. Good. Submit B. Got it. All right. We'll read C1 first. Is the tokens of type O do not appear in the input of the easy version. Okay, first of all, let me just say, so far, these problems have just been incredibly easy to understand. So, very well written. Ericto gave Monogon the following challenge in order to intimidate him from taking top contributions thought on Codeforces. The tic-tac-toe grid, there are n rows and n columns. Each cell on the grid is either empty or contains a token. Otherwise, there are two types of tokens, X and O. One operation, you can change an X to an O or an O to an X. Let X know the total number of tokens in the grid. You want to draw, at most, K/3 operations. Task is to make a grid, a draw. Oh, I see. What is a draw? Okay, diagonal doesn't count. Yeah, so it's all X's, it's easy. What if it has both X's and O's? Do the same thing. I might as well solve K1 or C1. Is it n by n? Okay. This be easier? Yeah, it would be. Otherwise, or if it's, let's say if it's equal to a dot. Okay, otherwise changes x plus y mod 3 plus, or at this xy equals an O. Okay, so the answer is chords at 0, 1, or 2. This is the answer. So we do this, then we do, along these diagonals. 1, 2, 3, 4, 5, 6, 7. Oh wait, 8, 9. 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, okay. 5 by 5, 1, 2, 3. No 3 in a row. Okay, I think that should be fine. How big can these be? 300 by 300. Okay. So I think we can submit this. C1. I did do C2 now. I think C2 might be a completely different ballgame. Or at least this solution has issues because you can have something like x, x, and then an O, and then 2 O's below it. And then that middle thing cannot win by itself. Oh, you can do this in one operation. You can change this. Yeah, so what I was doing before was superimposing O's on top of a grid. But now I need to superimpose X's as well, but I still only get a third of the tokens. Let's read problem D. Code cook. Each person has a rating graph, array of integers, updating the infrastructure. What? Updating the infrastructure, so you want to compress these graphs. Yeah, we know. I'm given an integer k. Program takes the minimum integer, the minimum of each continuous subarray of length k in A. Yeah, so this, then this, then this. So 1, 3, 2. Permutation, blah, blah, blah. Okay. Make it happy if it's a permutation. Given an array A, determine for all k, they will be happy if you compress it like this. So 1, oh wait, it's kind of weird. So if it doesn't have a 1, the answer is no. And that's an interesting example. 1, they're happy. 2, they're not happy. 3, they are happy. 4, they're happy, and 5, they're happy. But this is like deceptively complex. I think it doesn't get any more complicated than that case. Because usually the answer is for a big array and a medium k, the answer is always going to be like no, right? If you ever have this space between like, okay, if the 1 has a space to its left and right, then the answer is no, except for n. If you have a 2 with a space to its left and its right, then the answer is no. Oh wait, you could have 1, 2, 3, 4, 5, 6. This, okay, so this always is possible. Yeah, increasing is always possible. What if you ever have 2 of some number? Maybe we look at ones and we see we need exactly 1, 1. So you've got like these things, you've got things lower than it, you have things higher than it. Yeah, okay, so if we want there to be exactly 1, it's got to match the biggest difference between 2 infinities. If there's exactly 1. Yeah. Or, well, that's not true. For exactly 1 for a fixed size. So it's got to be at least this distance here. And at least this distance here. That's the minimum it can be. What's the maximum it can be? Maximum size allowed would be that. Anything else doesn't work. Okay, what if we have multiple copies of this number? It has to work for this biggest range, but not work for every other range. Yeah, so we have constraints for every number. We want the intersection of all the constraints. I think we can do that. Yeah. So we need the things we've processed in a tree set. We need all the things of our value that we're processing now. Then we process them in an increasing order and then add them all as infinities after the fact. And then we need the minimum of those, the maximum of the other ones. Yeah, okay, I think I can do this. Not without too much difficulty. You have to remember to go back sometime in contest and do C2 though. Up to n, okay. All right, array list integer array indices of the array list n. All right, so we've got this for I equals 0, indices of I dot add I. Okay, so we've got this. So now tree set integer of infinities or smallers. Yeah, that's what I want. There's new tree set. Static. It's a Boolean. It's an int array. Get bounds for int value array list integer occurrences, and then tree set integer bounds. Well, whatever. Okay, so we've got this. So we need to do that later. Bounds dot add -1, bounds dot add n. Okay. Value equals 0, value is less than n, value plus. Int array bounds equals the value would be the value, then we have indices of the value, and then bounds. Add all the indices to the future bounds. Okay, so then special case permutation, we'll do that in a minute. How do we get the bounds? Well, actually, maybe we do this now. So we need bounds for the numbers from 1 up to n. We need, for minimum, we need the minimum of u and everything smaller than u. Yeah. I equals 1 less than n plus. Bounds for at I 0 is math.max. Bounds for I 0. Bounds for -1, 0. And then this will be the min. Okay. N minus I. -1. This is what we're looking at. size will be I plus 1. Possible at I equals bounds 4 at I 0 less than or equal to size, and size less than or equal to bounds 4 at I 1. Okay. And then for 0, we need the permutation part. Array list in indices of if L that size not equal to 1 is perm is false, perm, then possible 0 equals true, and then print these out. Okay, for possible. 1, 0. That, what is this biggest matter? So this shouldn't be bounds for the biggest, not I. I need the bounds. There can be 3x. There can be 3 such x and 3 such o for one table, and the configuration is still winning. What? I don't know what they're saying. All right, so the end, PTR plus probably. Okay, so int left bound equals bounds dot lower. Then get this thing, and then oops, and then we also have the right bound, which is the higher one. And first will be this. So while PTR plus 1 is less than x dot size, and PTR and x dot get PTR plus 1 is less than the right bound, then PTR plus plus, and then last equals x dot get PTR. Good. So then we've got the left and the right. Okay. the right bound minus left bound. Minus 1. That's how big it is. Okay. So with the range sizes. And yeah, so then the second biggest range size will be we have to be bigger than that. So you have to be bigger than second smallest, or bigger than second biggest range. Smaller than the biggest range, or smaller than / equal to biggest range. And big enough that we only we have to be greater than or equal to this here. Okay. So the only thing we need to be smaller than will be range sizes dot get range sizes dot size minus 1. So we have to be bigger than range So that'll be impossible. Otherwise, if range size is that size greater than 0, then 1. There's 2. It's taking a very long time. Holy cow. Ugh, so long. Anyway. Yeah, then we, second last thing, we need to be bigger than that. Plus 1. Small enough that there is at least 1. Maybe we don't need to do this. Okay, and then what else? This part, we need to update the min. equals math.max of the min and last minus first. Yeah, min equals math.max of the min, or last minus, right bound minus first. And this should be last minus left bound. Yeah, I think that's fine. Needs to be that, needs to be that, okay. I don't think we need this actually. Because I think this is all the constraints we need. No, okay. So, let's print what these are. Min, injured, wait, what? Five to 5. So the minimum is wrong. Range sizes are just size 5. Yeah, that's right. So this is false. So the min. Ooh, what's wrong here? I guess we get to skip this if we are only the first element. Wait, no, this just is not right at all. What am I doing? We need there to be only one of us, right? This is why you think more before you start coding a bunch of stuff that you don't need. It's got to be that. Can't be anything else. Yeah, if we're not on the end, it's got to be that. If we are on the end, yeah, because if it's anything smaller, it doesn't work. If it's anything bigger, it also doesn't work. So this has to be the biggest one. Okay, what if we're only on the end? It's got to be bigger than or equal to second smallest range. Yeah, so it's got to be bigger than that. Otherwise, that's the only constraint. We can have two of us, but we never will. Otherwise, we're good. Is it always continuous? Yeah, I think it is always continuous. It's impossible because it's too small. It'll stay impossible because it's too small. The only difference is some numbers we just stop caring about. Okay. Try this again. So this get bounds is the issue. This part here. So if first equals last, and first is left bound plus 1, or first is right bound minus 1. Do one thing, otherwise do something else. Okay. As we have these range sizes. Okay, so then otherwise it can only be the biggest. This is hacky, but it might work, I think. Otherwise, yeah, we don't do anything. And now this is just the biggest it can be is the biggest minus the second biggest. Or it goes from the biggest to the second biggest. No, this doesn't work because it's got to be bigger than the second biggest range, actually. Range size -1 though. Yeah, so you have to be at least that. Or do you have 2? This is fun. One to 5, 1 to 4, 3 to 3. It shouldn't be 3 to 3. It should be 3 to something else. Yeah, it is 3 to 3 actually. 1 to 1, 1 to 1. Do we? Okay, so we do need a special case of this. Good. Took way too long, but I think we're fine. Submit to problem D. Pass pretests. Okay. Yeah, so I'm doing pretty poorly. I'm not doing too terribly. Okay. So, all right. So C has a whole bunch of solves. It's probably the next thing to go for, although it's not very many points. Okay, the geniuses just get it. The almost geniuses maybe go for some other stuff. Okay. No offense, Stephen K+, for me calling you an almost genius. You are very, very good. And I guess, yeah, it looks like the only people going for these hard ones are the geniuses anyway, so. Yeah, I think, oh, maybe I should read it. See what we're talking about? Struggling contestant. It's about me! They wrote a problem about me, guys. To help those contestants who struggle in a lot of contests, the headquarters of Codeforces are planning to introduce Division 5. What a meme. In this division, the tags of all problems will be announced prior to the round to help the contestants. On problems, the tag of the ith problem is AI. You want to solve all problems. To do that, you must solve the problems in some order. Included in extra limitations. You do not want to solve 2 problems consecutively with the same tag. Since you're afraid of big jumps in difficulty, you want to minimize the number of times you solve 2 problems consecutively that are not adjacent in contest order. Interesting. So you can start with this and then do them in order. So this is 1, yeah. 3. This one is impossible because more than half of them plus 1 are 7s. 7, 8, 7, 1, 7, 2, 7. Yeah, okay. This one is 2. It's the longest sequence of consecutive 1s. No, that's not right. Though it passes samples. Wait, what? I don't know, maybe. Go back to the C2 for a minute. They should have made this square, just saying. That's like my one criticism so far. This should be a square picture because all the inputs are square. Kind of brick brain at the moment. How do you do this? What? So you've got... So every time you have 3 in a row, you need to change one of them. So what if we force 1/3? Oh wait, we have issues then, don't we? Do we have this issue? Is this a problem? If we lock 1/3 of them, then we get to change one of these two. So if two things are the same, like if you have 3 in a row, if you ever have 3 in a row, oh, this doesn't work though. Spencer Compton's having a rough day here. Man, how do you do C2? Should I even worry about it? Am I spending too much time on it that it's not helpful? Alright, what's this comment? Quick break, quick break. What if SecondThread beats both of them? That would be funny. I would enjoy that. But we'll see. No. I'm not going for top contributor, you know? I'm going for... He looks a lot like Tourist. This is, Spider-Man, right? He looks so much like Tourist. I just realized that. Okay. Lots of memes. Anyway. This seems like turn it into a graph and then 2-color it or something. Oh, what if we 3-color the graph? Well, it's a problem because we only have 2 colors, right? So, can we always get... Can we always make 2 of these one thing, one the other? Oh, we can make one of them, make one O's, make the other X's? If we have a full grid, what does it cost to make one of the diagonals O's? Well, if they're all X's, then that costs 0 there. Oh, maybe that's it. Is that it? Oh, that would be cool if that is it. Do I have a proof? No, I don't have a proof. Maybe I'll make a brute forcer. This is cool. This is such a cool problem. Or if this is right, it's such a cool problem. Okay. If it's not equal to an x, or if it is equal to an x, continue. Otherwise, changes x at this plus plus boards x at this equals this. Wait, what if it's only on 2? These are all x's, these are all o's. Then pick one for that, one for the other. Yeah, okay. Okay, yeah, I can generate random data here. This if board at x, y is a dot, then continue, because we're fine with either. Otherwise, if board at x, y equals an X, capital X, and changes O at X plus Y mod 3 plus plus. Otherwise, do the same thing with changes X. That's a no. Okay. Good. Greater than this times, or greater than the number of things over 3. How do I do this? Okay, into number of things. Okay, it's greater than n things over 3, and continue. No. All right. So okay. So if board at xy equals a period, then sysout board or sysout a period. Else it's not a period, so we need to case this out. So if x plus y mod 3 is I, then we do one thing. Else if it's j, otherwise, we do this other thing. Okay. It's I, j, this. So this is board at xy. This needs to be yx. And then we need a new line here. Yeah, okay. Can clean this up a bit. Well, no. It's not. Okay, so then this is j, I'm making O's, and this would be X's then. This should never happen. And then if I find this, then continue test case. We did it. Ladies and gentlemen, we've done it. I think that's just a submit. Let's run it on samples for C1. For C1, it's the same thing. It's the same solution. Oh, that's so cool. Yeah, I think I'm going to take the risk and just submit this. Wait, do I need print writer? Some event does not exceed 300, so we should be fine, I think. Is this right? Oh, how many pretests? 10. Multi-case. So cool, I love it. Wow, that was a neat solution. Nice job, nice job. Okay. And now we read all the problems that are solved. Yeah, so read E, F, and H1. All right, not a terrible contest, to be honest. Could be going a lot worse. For first contest as IGM, I was mentally totally prepared to lose IGM. I still am. It's totally possible one of these is wrong. C2 is most likely to be wrong, I think. Yeah, but I don't know. Could have been a lot worse. Let's clean this up a bit and read E, F, and H1 and decide which one we want to go after with a strong bias towards F. A society can be represented by a connected undirected graph of M vertices and N edges. The vertices represent people, the edges represent friendships. So you've got the friend graph. This person has this income. A person is envious if the other person makes $1 more. A society is capitalist if every pair of friends is envious of another. What? Oh, yeah, that makes sense. Okay, never mind. I was thinking like friend cliques, but because then you can have like a clique of size 3 or more. So, but anyway, this makes sense because you only consider the edges. For some friendships, you know which friend is envious of the other. So you know which friend is smaller. Okay. For the remaining friendships, you don't know the direction. The income inequality of the society is the maximum. What is going on here? Maximum AI minus minimum AI. Oh, the max money minus min money. Okay. You know the relationships of friends, but not the incomes. It is impossible for a society to be capitalist with the given knowledge. Oh, if it is impossible for it to be capitalist, you should report it. Otherwise, you should find an assignment of incomes in which the society is capitalist, in which the income inequality is maximized. I'm a greedy capitalist pig. I like this problem. Okay, next next problem. Yeah, so this seems very two-colory. Parity is important. Is anything else important? Yeah, other stuff is important. You can have issues beyond parity. Okay. To help contestants who struggle a lot in contests, the headquarters of Codeforces are planning to introduce Division 5. Well, are there any crazy wacky bounds in the input? 200? Woohoo, so tiny. M is 2000. Smells like flow, if you know what I mean. Okay. Alright, I see. Struggling contestant. We read this. This is this weird permutation one, and it's 10 to the 5th. Seems a little bit caseworky, but not too bad. What is H1? Oh, multi-threading. They're end spools of thread. I love it. The spool comes in 2 types. The first thread. Oh. Man, I feel. Oh man, this wording is the greatest. They could have said the spools come in 2 types, white and black. The first thread is black, the second thread is white. Alright, cool. For any 2 spools of the same color, you can attach them with a thread of that color in the straight line segment. Okay? Define a matching as a way to attach spools together so that each spool is connected to exactly one other spool. Got it. Coloring, an assignment of colors. Coloring is assignment of colors to the spools. Coloring is valid if it has at least 1 matching. Okay. That is if the number of black spools and the number of white spools are both even. Oh, yeah, okay. Got it. So if they're both even, you can match both of them. Given a matching, we can find the number of times some white thread intersects some black thread. We can compute the number of pairs of differently colored threads that intersect instead of the number of intersection points. Okay, got it. Yeah, that makes it easier. So 1 intersection point may be counted multiple times to different pairs of thread, blah, blah, blah. Let C be the valid coloring. Let F of C be the minimum of such intersections among all valid matchings. Black, white, yeah. Matching the spools, intersection of colored threads. We've proven this is minimum possible. Okay. You're given a string S representing an unfinished coloring, black, white, and uncolored spools. The coloring C is called S reachable if you can achieve it by assigning colors to the unfinished spools without changing the others. This makes me so happy, Monogon. This makes me so happy. I'm so glad I read it too. Okay. Coloring C is chosen. Wait. What? Uniformly or random. Compute the expected value. We don't gotta minimize it? Okay. Okay. Wait, what is S reachable? Yeah, okay. All right. So, very complicated. We have this. We're going to color this. We've got like every possible way of coloring it. We want to know of all of those, what is the minimum number of intersections? Or like, yeah, for each way of doing it, what's the expected number of minimum intersections? Yeah, thank you. It's pretty obvious because Q is just 2 to the number of question marks. So we should be fine there. Oh wait, it has to be even, right? Among all valid ones. Yeah, so if you ever have an odd number of things, you skip that. So if you have an even number of things, you're interested in them. All right, cool. Oh, I really want to go after that problem. Oh, I want to go after it so bad. The problem is it only has 6 solves. And I'm no genius. Okay. It seems like F is not too hard. Moreover, lots of people don't find it too hard. So I feel like F is a good use of time. I'm gonna get a granola bar and go to the bathroom and think about this. What am I thinking about here? What's the minimum cost? We don't have to say how to do it. Minimum cost of permutation satisfies the requirement. So I was supposed to be thinking about this problem, but what I just noticed is these threads are arranged in a monogon. Amazing, dude. I love it. I love it. So good. Okay, anyway, back to problems I can actually solve. Oh man, such a good problem. Monogon, if you see this, I want to do an algorithms thread with you on this problem. This would be so good. This would be so good. Anyway. You've got this array with a bunch of places that we need to cut it. So in the first example, you have like 2, 1, 2, 3, 1, and then a 1. You have to cut it between those two. Then you want to join this back together. Like you've got a bunch of pieces, right? That you need to join together. So the answer to this is 1, because you need one cut, and then the start and the ends of these things are what matter. You can join it back together like this, because these are different. In the second example, you've got 1, you have a 1, then you have a 1, 2, you have a 2, then you have a 2. So yeah, does it always take the most popular? Okay, so you get it. Oh, okay, so you have to match all but 2 of these edges. But in addition to doing that, they need to be in a cycle, right? Like we can't make one circular and then make the other like a line. It's got to be a single line. How we match them. Would we ever want to do that though? Is that ever even helpful? I think you could always splay them. Like if you have a line and a circle. Without pictures, this probably makes no sense. But if you have a line and a circle, then these differ every pair. These also differ in every pair. So you could just like cut this open, and the difference, cut these open, and then it matches one of the two ways because they're different. When is it impossible? It's impossible if, so you have 4, you get 1, 2, yeah, so it's n over 2 ceiling is the max for any one thing. So if it's bigger than that, then it's impossible. Hang on, is there, let me look at the standings real quick. Is there any reason for me to go for H? No. No, no reason. Yeah, it's just, it's too hard. Oh, one sec. Yeah, so despite being an awesome problem, it's just not strategically smart. Wait, what is H2 then? 3 colors? No. Oh, there are no updates. You update the color or something? Oh, yeah, okay, weird. I see, interesting. If I lose rating here, I'm totally fine with that. Like, really, losing anything less than 22 rating, I would be ecstatic. Hopefully, we can solve F and gain a bunch of rating, though. That's the plan, because we're getting pretty close here. So, how are we looking? We're looking all right. If we have more than n over 2 of anything, it's impossible. Otherwise, it's definitely possible. So, yeah, we just need to remove this and something else. Okay. We don't have to actually do it, yeah. So, whatever pairs are left. Wait, what are we doing again? Oh, increasing the cost. Yeah, it's the number of pairs that are left, right? So we have 1, 1, 1, and 2 are the 4 sides of this thing. Oh, pairs that are left divided by 2. Or things that are left divided by 2, yeah. So n, I guess, n things, like n unmatched divided by 2. Okay, this one has, we've got 1, 1, 1, 1, 1, 2, 2, 2. So we match a 1 and a 2 to itself. We match a 1 and a 2. Oh wait, no, okay. N things minus 2 divided by 2, because we don't need 2 of them. Yeah, okay. 1 and the 2, the 1 and the 2, and we're left with 2 1s. That's fine. Yeah, okay. This one, we have 7. Okay, let me just write it out. 7, 7, 2, 7, 7, 1, 8, 7. So we cut here, here, and here. But it's impossible, so we skip it, okay? This one is 1, 2, 3, 4, 1, 1, 2, 3, 4, 1. So we cut here. And we need to make one other cut. Yeah, okay. That's good. Doesn't seem too bad, actually. For those of you wondering what this is, I lost to Colin in a duel. I'm sure you've heard about it. If not, I made a video about it, like summarizing what happened. And it's a pretty good video, but he's also worth subscribing to, for sure. And cuts is 0. Then A. For test cases, I think we're probably fine here. Oh, 1 second. Okay. Did we have a 1 second time limit with this? That was for D. What was time limit for D? 2 seconds. Good. Okay, so then print -1. Yeah, because that's impossible. Okay, good, good. Otherwise it's possible. Yeah. Endpoints or array list integer points is new array list. Zero. Add 0 endpoints dot add a -1, and now for and I equals 0, I plus 1 is less than n, I plus plus. If a at I equals a at I plus 1, then we need to cut here. Endpoints dot add a at I twice. I guess we'll add a plus 1 so it makes more sense to us. And now we have all the endpoints. Okay, so now for I and endpoints, then frequency dot add what? Frequency at I plus plus. And then we want to see if anything. Oh, we want the max. Yeah. I, if max times 2, okay, what is this exactly? So this is always even, so we don't need to worry about odd cases. So, yeah, okay, what do we do here? Oh, we also need to say ncuts plus plus. So we cut something open. Okay, now ncuts plus equals mat.max of 0 and something. This is going to be endpoints.size and others equals size minus whatever is most frequent. Max minus others over 2, I think, maybe. Max minus others minus 2, because we get to skip 2 things. Over 2. Can it be odd? Can be odd. We can have 3, right? 1. Yeah. What do we do if we have 3? Then we can match these 2. Oh, they're the same parity. Yeah, okay. So this is fine, because these two are the same parity. Yep, and then sys out and cuts. Should pass samples because we just tried it. 1, 3, continue. Test case. Do we think about this for a minute before we submit in case we're wrong? I feel like I haven't been wrong in a while. Might be refreshing, you know, just in case. To be wrong once in a while. Not yet, not today. Well, honestly, not bad. Not bad. We're caught up to geothermal here. Not bad. So now, it might make sense to do H. Yeah, I'm not going to read G. Because Tourist solved H like almost 45 minutes ago. So he's read both of these, and if Tourist can't solve it, I don't think it's worth my time. And also like a bunch of other LGMs. So even if Tourist is having like an off day, like it's probably just not super helpful. Okay. Yeah, man, C2 was hard to prove. For sure. I don't know what was up with that. So I think it's a toss-up between H1 and E for the rest of my contest. What was E again? It looks like I might keep IGM, which would be super refreshing. Yeah, man. Whew, nice. Nice, nice, nice. E. What is E? Oh yeah, this one. Bounds are so tiny. Scary. Okay, there's E and there's H1. You know, as much as I would love to solve this problem, it's very, well, I don't know, is it math heavy? Maybe it is, maybe it's not. So, okay, let's give it some fair shot here. If we have an odd number of consecutive things, yeah, all that matters is the group sizes. Is it ever more than one? It's never more than one. Why would it be more than one? Oh, it would be more than one, because you have to match blacks with blacks, whites with whites. So you can get, if you have like black, white, black, white, black, white, then you're gonna need several intersections, I think. We have 8 things like this, then you have to go like this. Oh wait, yeah, doesn't matter. You still need 2. There's a bunch of, man, all these problems feel like they're parity observations here. We've got like, there's definitely parity stuff going on here. For E, it feels like it's 2 coloring-ish. And for the problem I just solved, it had parity math here to make sure this worked. Maybe this wasn't part of the solution, but still interesting. Yeah, what do we do here? Is it like the number of odd groups over 2 or something? Well, here there are 8 odd groups, and the answer is 2. So those seem pretty unconnected. What about this? We have 4 odd groups, or maybe over 4. Yeah, because the number of odd groups has to be even. You definitely need an even number of odd groups. Do you? No, you don't. N is even. N is even. So you need an even number of odd groups. And wait, this is weird. You can have white, white, black, white, white, black. That's weird. Okay. Yeah, that is really weird. Maybe this gets a bit harder. So what if you've got like white, white, and then black, white, white, black. So now these handle themselves. And then we'll have a black here. Then we can have we have 2 blacks, 3 whites, 2 blacks, and then a white. Yeah, so now these will pair up like that. These pair up, and then you're fine. I think this is challenging. Let's think about you for a minute. Why am I wasting time looking at the scoreboard? I don't know. Not sure. Just kind of interesting. Man, what's going on? No one from UCF is competing anymore. Why? The fools, I tell ya. The fools. Vertices represent people, and edge represents friendship between people. Yeah, friend group, you know the direction of some edges. Okay, yeah. Let's do some examples. I remember, I think it was Global Round 9, the examples were all trash, but in this case, they might be helpful. 1 to 2, we don't know. I guess I just won't draw arrows here. 1 to 2, then we have 3 to 2, 2 to 5, 6 to 5, 6 to 3. Oh, I've drawn this poorly. 6 to 5, 6 to 3, and 2 to 4. Okay, we know 2 to 4 is an arrow, and we also know 6 to 5 is an arrow. It's a good example, I think. So it's 2 colorable. We can do that. Does the fact that it's 2 colorable mean anything? Yeah, it does. It means it's not immediately impossible. Because if it's not 2 colorable, then it's impossible. Yeah. So we've got a bipartite graph. so it doesn't matter how we direct these things. Okay. Yeah, there are a bunch of ways of doing this. We need all paths from a node back to itself to be equal to 0. Is that right? Kind of. It's kind of tricky. Add that edge, that would make it a bit more complicated. If we add an additional edge from 6 to 4, does that tell us anything? Maybe. Man, it feels so flowy. We've got a bipartite graph. We've got small bounds. We need to assign. We need to like pick some edges. Well, connected components we can separate, right? So separate connected components. Because they are independent. Yeah, thank you for this, not guaranteeing anything. I appreciate it. Good problem writing. I mean, all these problems, they're all well written. They're all interesting. Yeah, I really like them. So these global rounds are good. It seems like the kind of thing where once I figure it out, it'll be like 20 seconds. The code for flow. Just set up the graph. I guess I have to extract it, so it'll be maybe 20 minutes, but still. Flow with circulation, is that it? Is it circulation? This is 1. It's more like anti-circulation, really. Yeah, I'm running flow on the wrong stuff. Oh my goodness, this guy came out of nowhere. Oh, it's an alt. I wonder if it's Mufa Fabio's alt. Stop making alts, people. Come on. Use your real account. Let's draw this as bipartite then. How about that? 6 and 2, and then we have 1, 3, 4, 5. So 6 has a line to 5, and then an unknown to 3. 2 has an unknown to 5, 3, 1. And then a known to 4. So if we set this as 0, then this 5 has to be a 1. Two we could set as either 0 or 1. So is the issue is always going to be between two things on the same side, right? That's what would make it impossible. So like if 2 were envious of, if we had a 2 to 3 edge and a 3 to 6 edge, the issue is now like this 2 to 6 is a problem. Can we run simplex? And hope it's an integer. Who knows? Who knows? That would be a hack, wouldn't it? It's kind of the classic. Oh wait, so we want all of the edges, if all of the edges go to the right, then that's easy. Yeah, if we can direct all of the edges to the right, that would be fantastic. The challenge is, what if we have edges we can't direct to the right? Yeah. Ooh, that's good. That's good. That's good. That's good. So initially, direct all edges to the right. But then, what happens if we direct this edge this way? Okay, yeah, I think we're onto something here. Okay, so direct all edges to the right. Now if you have an edge that's forced to be to the left, then this thing needs to be, like, you can't have any paths from something on the right, or you can actually have those paths. Yeah, you can, but something's got to change. What changes? I think I'm just reinventing the problem in a way that isn't helpful. I'm not like simplifying it. I'm just like trying to force it into a box that it isn't naturally in. Like I'm trying to make this into a bipartite graph problem. And I guess you have a bipartite graph, but like maybe the fact that we're assigning values to each node is more important. Steven's got it. All right. So what if we just kind of like do it? Like if you have no in degree, you might as well just make you 0. Right? Make you 0, direct all of the edges out. What if nothing has no in degree? Then we're stuck, and we also didn't make any progress because that's a very easy case to make. You just pick the thing and make a circle. Okay. So we pick something, we make it 0. We don't know anything about its edges. Man, it just seems like there's so many steps to take. I don't know which one to take. There's definitely something going on here that I don't see. Like, there's this graph with a lot of properties. What properties are there? It's bipartite. Bipartite, we have a bipartite graph. We want to direct some of the edges. Yeah. We want to assign weights so that the edges, that all the edge paths are decreasing, or I guess increasing paths, yeah. Increasing by 1 even. We need to go from the 3 to the 6. And also from 2 to 5, let's say. Or let's say 5 to 2. Yeah, okay, why is this tricky? It's tricky because we don't want the flow to be 0. Yeah, the way that we're directing edges isn't like make the flow 0. Okay, we don't want the same amount coming in as coming out. We want all paths to us to be height 0. So the constraints are that things that are adjacent have to differ by 1. Some things have to differ by 1 in a specified direction. We can't do 2-sat on the heights at least. Can we do a DP? No, there's just too many things to keep track of. Because, like, the part of the, yeah. Capitalism is so difficult. All right. So if we were communist, we want everyone to be equal. Oh wait, we also, hang on. Flow doesn't work at all because we want to maximize this, right? The maximum possible inequality. We want to maximize the inequality. If we wanted to minimize the inequality, would that make it any better? Well, I don't know. Maybe this is the same difficulty problem. So suppose we start communist and we want to become capitalist. For communist, everything on the left has 0, everything on the right has 1. So all the edges go right. Okay. Now if we want to make one edge go left, want to make an edge go left, then we do that, okay. What did that change? That just made this a 2. We can't have an edge from a 2 to a 1, that's fine. But it changes the direction of these edges. It changes the direction of that. So we can take one node. If it has all outgoing edges, we can make them all incoming. That is equivalent to +2 in the graph. That's the only thing we can do. So if it's got all outgoing edges, we can make all the edges incoming. That's a +2 to the answer, as long as one thing stays at 0. Yeah. So if this 2 is going to stay at 0, well, we don't want a 2 to stay at 0, we want the 1 to stay at 0. So let's make these, maybe we brute force which one stays at 0, so these are all 0. And then these are initially 1. So first we can increment the, oh wait, we have certain edges that need to be going one way or the other. Okay, we can also pick an entire set. Yeah, so that's one thing we can do. We could also pick some set and increment the entire set. The set needs to have all incoming edges, and then, or all outgoing edges, and they become all incoming. all outgoing edges. Make them all incoming. Okay. What if, well, that's tricky because we've got duplicate constraints. We pick some set of nodes where all of the edges are going into that set. Take the entire set, so all the edges inside don't change, all the edges outside, but all the edges that cross the set. Seems like I'm in cut. All the edges that cross the set, we change. We want to do this as many times as possible. How do we find a solution at all, though? Can we BFS? What if we just repeatedly keep trying to fix things? Does that work? Yeah, maybe let's try it. So we have, maybe it would be more interesting if we go the other way. So 1, 3, 4, and 5 go to 2 and 6. Six goes to 3 and 5. Both of these are, or 6 to 5 is forced, and 6 to 5 is forced, 2 to 4 is forced. So initially these are all 0. These are 1. So this edge is fine. This edge could be fine, I guess. This edge is fine. This edge is fine. This edge is not fine. So if an edge isn't fine, I guess just increment this thing. So this needs to be at least 2. Try again. This is fine. This is fine. This is fine. It's fine. It's not fine, so we need to increment this. That's 2. That's fine, that's fine, that's fine. Yeah, so this works, this works, this works, this works. That's okay. That's also okay. So that's a solution with a inequality of not very much. So I guess now we direct all of the, so now we have a solution. Yeah, does that always work? I think that always works. We're only incrementing things when we're forced to. Yeah, okay. I think that won't be an issue. N is small enough we can do like an n cubed or something. Yeah, because we're not making any decisions that are smart, and we never decrement anything. Okay, yeah. So now we have a solution. So now direct all of the edges as we need to. Or as they are. Okay. Now repeatedly we need to select something, select some group. That only has incoming edges and increment it. Or only has outgoing edges and doesn't include node 1. Okay, now select some group. Well, not necessarily node 1, but some node that we want. Some question mark node. And we want to flip all edges, flip the set, or like increment the entire set. So what does that mean? That means all edges go from outside the set to inside this, or from inside to outside. Yeah. Like all cross edges. Go from inside to outside, and we can modify each of them. Okay, that means anything with any in degree can't be chosen. It can be, they just all have to be chosen. It and the thing it comes from needs to be chosen. This 3 has a lot of out degree, but it doesn't need that much out degree. So we can increment the value of 3, right? We can do that. Which edges were forced? 6 to 4 were forced. In the sample we had 6 to 5 were forced. So this one is forced. And 2 to 4 is also forced. So yeah, we could increment this 3 if we wanted to. How do we find a set that we can increment? We want to find some cut of the graph that follows a bunch of restrictions. Do we run flow a bunch of times? Man, this does not seem like the right solution. This seems like I'm doing really sketchy stuff all of a sudden. Well, okay, if we have a fixed edge, then we need to join these two things together, right? Because we can never separate them. So these get joined into one node. These also get joined into one node. Because, well, okay. So, yeah, so we need to cut the graph like this. So we want to add 2 to this. I see. I'm fixing the wrong thing. Maybe that's the problem. So here's node 1 with a 0. Okay. So this is locked at height 2. Okay. All right, and then we increment. We've got like a cut. What? Oh, is this like Dijkstra's? This feels so much like that one n cubed thing. Hungarian. Feels like Hungarian. But I have no idea why it would be anything like Hungarian. Other than that, we have a bipartite graph. We're trying to maximize something. What does Hungarian do? We want to find the minimum cost when we have cost of each pair, like minimum matching. We have the cost of each pair. When we have to match everyone. Other hacks? Not yet. Oh man, but both these problems I should get. It's an interesting scoreboard for sure. I mean, honestly, this is, if it ended now, it would be a perfect set. Looks like there's a very real chance to resolve H2 though, so maybe not. If we like make someone the smallest, we know who that person is, then that means all of their edges go out. So we've got a bunch of edges decided. Any pairwise edges from those we also know. But that doesn't really tell us anything, because now we have like a bunch of other decisions to make. Oh, maybe it's just a BFS? Where's that? Okay. Feels very BFS-y, but we don't know where the start point is. So we've got a start point BFS and some negative edges. And some edges where if we go the wrong way, we subtract one instead of adding one. Otherwise, it's just the distance. Oh, maybe that's it. Man, maybe I'm just stupid. Do a BFS from some node. Okay, let's try this again. 5, 6, 4, 2, 3, 1 here, 1 here, 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 and here. Okay, so we do this BFS. So we've got 0, 1, 1, 2, 2, what? 2. So 6 is where we start. Try again. So we pick the right starting point, which we'll do by brute force. Okay. So we got 0, 1, 1, 2, 3, 3. The problem here is we might have some edges that go the wrong way. In this case, we need to find some cut of the graph that includes only wrong edges and non-edges. Okay, what are my forced edges here? 6 to 5 and 2 to 4. Those happen to be right. Does it change anything if this is forced? It doesn't. It doesn't change the answer. Okay, we need to find some set of wrong edges. Or find set, I guess a cut. Across non-edges and edges that go from inside to outside that should go from outside to inside. or wait, no, we want to decrease it. So they go from out to in. So initially we just pick an edge, or just pick a node that's wrong, and now we expand the set as long as we need to. And then decrease all of those things by 2. Okay, we have a solution. Good. 20 minutes left. I needed 20 minutes. I have 19, so we might be in trouble here. Okay. So what's the runtime here? We brute force a start point. That's order n. Then we're BFS. That's okay. That's order n. Then n times we find a cut and fix stuff. So yeah, that's like n squared. We find a cut, fix some things. Heights are at most n, so we, I don't know, it's probably about n squared. It's probably about n cubed, probably. Yeah, I think that's fine. Okay, so BFS, yeah, that's fine, that's fine. When do we need to include something? So what does this BFS look like? So we pick some node, or we find an edge. Yeah, pick like the wrong part of an edge. Pick wrong edge dot from. Like currently bigger. And then anything that decreases towards it. So include adjacent that decrease toward it. And also include predefined. That increase predefined ones that increase away, or that increase towards it. That increase towards, yeah. And then decrease the set. And keep going, and then at the end we verify. Or if it takes too long, yeah, when does it not work? Why does this not work? If we do too many steps, or I guess if after this we have a cycle. Yeah, when does this not work? If this doesn't cut the edge we're interested in, we have a problem. Because then there's like a cycle of dependencies. I guess we have to start coding it, whether we like it or not. I'm not ready to, but if I don't start coding now, I'll run out of time. Okay, wait, I don't understand. When would this be impossible? Oops. Brute force the start for some start. We check. Yeah. Okay. Let's just start. Okay. Here's problem E. We're gonna need a node. We're gonna need an edge, right? I guess we probably don't need an edge. Yeah, we do need an edge. Node 2. So then this will have an array list edge of edges, and probably an ID. Okay, is this multi-test case? No, it's not. Right, and then okay, so if C equals 1, otherwise we do something else. Then nodes at A, dot edges dot add, new edge to nodes at B, and predefined is true. The other should be bigger is true. No, the other one should be smaller. So this should be false. This is A and this is B. In this case, we do the same thing, but these are all false. Yeah, okay. Okay, so then, yeah, this sets all the heights. Returns inequality. Inequity or inequality? Why does it matter? Inequality. Worrying about the spelling of. Okay. My comment. Okay, so for int test root 0, test root less than n, test root is plus. How much time? 10 minutes. I'm not going to finish. Solve the nodes n and test root. Solve this. Okay. If res greater than best, then best equals res. Test root equals best root is the test root. If best equals -1, then print no. Return yes. Sys out the best, and then sys out n can be 1. Okay, that's kind of annoying, but whatever. Print the heights. So for node n nodes, sys out n dot height plus 6/2. So we don't have to worry about negatives, and then this should be space separated. Okay. Okay, this is solve nodes and best root. So we have the best thing set here. Okay. So we should be good. Okay. How do we do this part? Start with a BFS. Array deck node nodes. Array deck. This is BFS. Yeah. BFS dot add nodes at root. Well, okay. Also, for node and nodes. Wait. We've got multiple components. This is obnoxious. Okay. Is it guaranteed to be connected? There we go. Thank goodness. Okay. How much time? 8 minutes. Not gonna finish. Darn it. And dot height equals -1. Nodes at root dot height equals 0. Well, not BFS dot is empty. Node next. BFS dot remove first. Edge E in edges. Next dot edges. E dot 2 dot height equals -1. E dot 2 dot height equals next dot height plus 1. E dot 2. Oh, also, what if it's not too colorable? Will that be an issue? I don't know. Maybe. Who knows? Yeah, it might not be too colorable. Okay, E dot BFS dot add last E dot 2. Keep doing the BFS till we're done. Okay. So now we need to have these edges. That might be helpful. Edge we would like from. A. Okay, we'll also have an edge array edges, do an edge array M. Required. Test root, this is an array list. Edge required edges. Okay. So now keep fixing required edges. Counter is 0. Counter is greater than, I don't know, whatever. Don't worry about it for a minute. Okay. Okay, so public boolean broken turn. Okay, so now we can check this quick. Definitely not going to finish. Yeah, okay, so now alright, so now for edge e in all edges, if e dot non-bipartite minus 1, yeah, okay. Okay, so now we've tested for this. Blah blah blah. Okay. All right. So now we know it's bipartite. Now we need to fix things. I don't have time. Okay. Unfortunate, man. Yeah, I don't have anything I can fix here. So close, but I can't do it, and I need like another 5 minutes at least. Plus this likely is bugs that I'd have to figure out anyway. So close. Yeah, I've got to do a BFS, and it's just not enough in that much time. Well, it was a good round. I enjoyed the problems. It was very clever. Yeah. It looks like I might... Well, it looks like unless I fail system test, it looks like I'm keeping IGM, which is nice. Makes me very happy. Yeah, and my friends do. Ben Q, nice win for sure, man. This is revenge for Hacker Cup, I see. Andrew He, that's not bad. Solved all of the hard problems. Now he's on to the easy ones, I guess. Kevin, nice job. This is an interesting scoreboard. It's almost perfect. If Ben Q didn't solve set, it looks like it would have been perfect. I think like for a Codeforces round though, this probably is perfect. If you have exactly one person who solves set, I think that's about as perfect as it gets. It's hard to beat that. Yeah, and then he went for hacks after. So, nice job, Ben. Then you had Andrew He getting everything but problem C. That's good. Somehow we still lost points though, but oh well. This guy came out of nowhere. I think this is an alt. Maybe Mifa Fabio. Maybe he picked up this alt after like retiring. Okay. Let's go over solutions then. So, got some time here. I thought it was a very good contest. I enjoyed all the problems. Did I read G? I don't think I read G, but I read everything else. Oh, and this one's communism. Okay. Yeah. So, good set. I liked all of them except G, I guess, which I didn't solve, and then H1 and H2 I didn't get time for. But I can talk about solutions to more or less all of these problems. I guess my E solution is a bit sketchy because I haven't actually AC'd with it, but the rest of them I can give solutions to. So if you're interested in that, stay tuned. And here we go. Problem A, avoid trigub. Let me get my drawing pad out quick. So in this problem, you have some string, and you want to remove some characters from that string so that it doesn't contain the subsequence trigub. Now, there are a bunch of ways to do this. One thing might be you can just take all of the R's and put them in the beginning, for instance. For me, I thought it was easiest to just sort the string. So if you have some array, you can just sort whatever that array is. And you know, if the letters are sorted, you'll never have a Y followed by a G, because Y comes after G in the alphabet. So yeah, so if it's sorted, you'll never have a Y followed by a G, so you'll never be able to make this trigub. That was my observation for problem A. The code is pretty clean. You read the array, you sort the array, then you print out the array. This prints a string in Java, so it's super clean. And then you also have to read this integer to get it out of the way. Yeah, that's one idea. There are probably lots of other solutions as well. They all work. Problem B, balls of steel. So you've got a bunch of balls in this problem, many balls, and since your balls are made of steel, it's very attractive. So you might have different balls come together and attract each other. In particular, you get to put electricity into one of the balls, and then all of the balls within the Manhattan distance of K will go toward that ball. So there's one important observation here, and that observation is, get me some space, please. That observation is that if you've got, say you've got two balls like this, if you activate this ball in the middle here, everything within Manhattan distance of K will be in some diamond shape. So this distance here will be K, this distance here will be K, and then any path that's like up and down here to this edge will also be a total of K long. So the thing to notice here is that if we have these two balls and we activate this first ball, everything within this distance will then be at this ball's position. Then in the future, if we activate some ball outside of this range, like if there's any ball outside of this range, these two are more than distance k apart, Manhattan-wise. Which means they'll never be able to join together. So if we can't like combine everything in exactly one move, then it's not going to be possible to do it. You can't like you might think, okay, you've got a series of balls that are like this, and they can't all reach each other, but you could like move this one over to here, and then you could move both of these over to here. But the issue is, if you activate this ball, then you'll move this one over, and now this gap will be too big. So yeah, the key observation here is the answer is going to be either one move or it's impossible. And n is small enough where we don't have to think or anything. We can just try all of the possible moves and see if they would work. So in code, what that looks like is we read in n and then the maximum distance k. We read in all of the points. And then I, for me here, is where I, like the ball that I'm going to activate. And then j is all of the other balls. So for every pair of balls, I check if their Manhattan distance is greater than k. If it is, it's not every pair. For every other ball compared to ball I check if that would be too far of a distance, if they wouldn't be able to attract each other. And if so, then this is impossible, right? Then ball I would not be a valid thing to electrocute. So I skip it. Otherwise, ball I would work. That takes one turn, so then I print it. And that's a solution to problem B. Okay, very cool. Problem C. Now I've got a proof for C1. I don't have a proof for C2, although I have like the intuition for it. So the proof will be an exercise left to the reader, as usual. So what is C1? You've got a tic-tac-toe board where diagonals don't count. So 3 in a row horizontally, 3 in a row vertically. The board isn't necessarily 3 by 3. It can be like 100 by 100, I think, up to 300 by 300. But it is a square, which makes reading an input nice. And you're going to do some things with it. Namely, you're going to change a bunch of moves so that the game doesn't have a winner yet. So there are no 3 in a row X's, no 3 in a row O's. And the restriction is you can change at most 1/3 of the elements. So you can change at most 1/3 of the things that exist from either X to O or O to X. In C1, they're all X's. So you want to say, okay, you got to change some X's to O's. Effectively, you got to delete some X's. And you want to make sure after you do that, there are no 3 in a row. No 3 X's in a row that are left. So how do you do that? Well, here's the idea. Let's imagine we have like a full board here. I'll just draw a 4x4 because it's kind of easy. What we can do is pick the diagonals and color them like this. Then blue, then red, and then yellow, and then blue. So what you can notice here is if you pick any 3 in a row, horizontally or vertically, maybe I'll pick these 3 here, that will use 1 blue, 1 red, and 1 yellow. Now, the thing with this, what makes this nice, is if we delete all of the blues, right? If we delete everything that's blue, then you never have any 3 in a row, because you know that any 3 in a row will use a blue space, and there aren't any blue spaces. So we've like covered that. So that's the solution to C1. You can delete all the blues, or you can delete all the reds, or you can delete all the yellows. One of those 3 is going to be the smallest. Whichever one is the smallest, that's how many you delete. So like you have 3 numbers, you have A, B, and C. They're all integers. A plus B plus C equals, I think they called it K is the number of things. Yeah, equals K. So the smallest one of these is going to be like the min of A, B, and C is less than or equal to K over 3 floored. And that should be pretty intuitive. I don't have a proof for that, but I'm sure mathematically if you could find something that works as a proof. Now, yeah, okay. So I said these were all X's. They might not all be X's. Some of them might be blank squares. But like if you have blank squares, like that's fine. you can just not worry about it, right? And you just count how many x's there are total. So here the yellows have 3 x's, the reds also have 3, and the blue have 4. So you could pick yellow or red. Both of those would be k over 3 floored or less. So if you delete all of the reds here, right here, like the, if you delete these, then you have that sum valid solution. Okay, cool. So now how do you do it when there are O's? This is a bit more complicated. And you can't like initially the thought that I was trying to go down, like the road I was trying to go down was you take like one of these colors and you turn them either all to X's or all to O's. But you have an issue here, which is you could have something like this. So if the diagonal we pick is this diagonal here, we have trouble because we need to turn this thing. If we turn this into an X, then we have 3 in a row. We've created 3 in a row. And like we have another issue, which is like we need these, I guess, like there is a way to do this without changing 2 different things. So we would need to change this to an X. That would be one way of doing it. And now we have solved it with just changing one thing. So that's one solution. Another solution would be this. So yeah, so it's like, it's kind of tricky because if you make this an X, then you have to make one of these things an O, and that's 2 moves. So you have to be careful, I guess. The key observation is we can actually still use this same solution. But what we need to make sure here is one of these sections will leave as like half X's, half O's. One of these sections will change to all X's, and one of them will change to all O's. When I say all X's, I don't mean every space in that needs to be an X. I just mean every space is either an X or it's a dot. So in other words, one of these sections can't be used by O's, and one of them can't be used by X's. And it turns out there's always a way to do that. So the reason why is, I guess, not super obvious to me, but if you do some examples, you can like convince yourself of it. The other thing to keep in mind is like, okay, you've got these 3 sections, right? Let's say one section is like all X's. So if this is like all X's, then we'll make the group that's X's be this. So we don't want this to be all X's. Worst case, and like if all 3 of these are all X's, right? Let's say these are all X's, then we're gonna spend whichever one has the fewest X's, we're gonna turn all of those to O's. But like, that means worst case, like they're all about half and half. So worst case, we'll make like half of these X's, these will be X's, and these ones will be O's. And that's like worst case. We'll have to change all of these X's and all of these O's. And on total, we're changing like k over 3. Right, so we change about a third. And like the math works out that it's always gonna be less than k over 3. Of all of your choices, like if one of them, like as one choice gets worse, another choice gets better. So you'll always have some choice that's good enough. And this wasn't obvious to me, but apparently it was obvious to people who are smarter than me. So yeah, that's kind of fun. What does the code look like that for this? So for C1, okay. For C, yeah. So here's what C looks like. I have the board, and then I have these 3 boards. The first board is like what the board will look like if I change all of the X's on X plus Y equals 0 mod 3. So this is like, if I change the things on X plus Y equals this index mod 3. So either X plus Y equals mod 3 is 0, 1, or 2. One of those I won't allow any X's on. So yeah. Then I worry about that here. So if there's an X on whichever diagonal that I'm setting to 0, that requires one more change, and I turn it to an O in the board that I print. Then finally at the end, I take whichever one is the smallest, whichever one requires the fewest number of changes. For C2, I have a similar strategy. And for C2, I just I simplify, I guess, how I do the logic here a bit. But I just say how many changes, like if I changed X, like these are the 3 diagonals, right? So it's if I change this first diagonal to be x's and dots, then what would it look like? If I change it to be O's and dots, like how many changes would that take? And then at the end, I'm like, okay, there's one diagonal that I'm going to pick to be x's and dots. Another diagonal is going to be O's and dots. And I want to find one pair that's legal, that does that legally. So yeah, and they can't be the same pair. Can they be the same pair? No, they can't be the same pair. Because if there's anything that isn't a dot on it, then it's either an X or an O. It can't be neither. So yeah. Yeah, so this keeps track of how many changes there would be for each diagonal. And then when I print it, it's just a whole bunch of casework. If it's a dot, it stays a dot. If it's on the diagonal that I picked to be X's and dots, and it's not a dot, then it's an X. And if it's the diagonal that I picked to be O's and dots, and it's not a dot, then it's an O. And if it's on neither diagonal, it just stays whatever it was. Okay. All right. Cool, cool, cool. Enough of that. On to problem D. What was problem D? I forget. Rating compression. Yes, this problem. Okay. So this problem was not too bad, I think. You just had to be careful, I guess. So a good example would be like, okay, so yeah, so what's the problem first of all? So you want to solve a series of problems. The problems are given to you in increasing order of difficulty, but you don't want to solve any two problems in a row that are, wait, that's the wrong problem. Nope, JK, ignore me. Yeah, okay, forget that. You have an array, and you're going to take, like, for each value from 1 to n, you're going to take every subsequence of that size in a row, and you're going to see if that makes a permutation. As an example, the array 1, 3, 4, 5, 2, if you take arrays of size 3, the first array will be 1, 3, 4. The next array will be 3, 4, 5. The next array will be 2, 4, 5, or 4, 5, 2. The minimum of this first array is 1. Of the next array is 3, and of the third array is 2. So this is 1, 3, 2, which has each of the numbers from 1 to 3 exactly once. So it's a permutation. So the question is, if you do this for every size, which ones of those are permutations and which ones aren't? Okay. So, if you do it for things of size 1, well, special case that's very easy to check. Because for things of size 1, if it's originally a permutation, then it's a permutation at the end. So that's very easy. Doesn't change there. For things that aren't of size 1, let's look at like some particular number, right? So each number is going to have some constraints on how big the range is allowed to be. Let's say we're at the number like 5, for instance. We've got maybe some 5s here in the array. If we've got numbers bigger than 5, they don't really matter. But if we have things smaller than 5, any range that we pick, if we want that range to be equal to 5, the things smaller than 5 can't be anywhere in the range. So if we have like a 1 here and like a 1 here, for instance, any range we pick, we're only interested in things that only contain things that are 5 or bigger, because we want 5 to be the minimum. So for this range, for instance, we have a concern, which is it has to be, like, if it's any bigger than this size, this range won't be relevant, because neither of these 5s will be chosen. Any range that's bigger than this will always either include this one or this one. Okay, so yeah, so like we're only looking at things that are this big or smaller. Now we've got 2 5s in this range. So we have an issue here, because if we look at something that's 1 smaller than this, a range that's like just this big here, then this will be 5, but also if we move this over by 1, this will also be 5. And this means if we compress something of this size, there will be 2 5s in the array. So that's an issue. Which means anytime you have some block where you've got like something less than you and then 2 of this element you're interested in, 2 or more, and then something bigger than you. If it's possible, either the answer has to be bigger than this block, or it's got to be equal to this block. So that way you have exactly 1 5. Or you can't have any 5s in the array at all. Okay, so that's some constraints. Let's worry about the case where we don't have any 5s in the array at all at the end, and then we'll handle that later. But so what's this constraint? Well, okay, we've got this thing here, which is we know if there are 2 5s here, it's got to be exactly equal to this range. Now I said that that's not entirely true. The reason why not, actually it's got to be greater than or equal to this range formally, but the reason it's like this, or the reason it might be able to be greater, is because we might have some other range later on which has a similar constraint, right? So we might have 2 5s here, but like a 1 on both ends of this. Let me move this down. And in this case, it's got to be equal to this bigger range. Now this smaller range is totally irrelevant. Like we don't care about it at all. There's one case in which it acts differently. So if you have a 5 anywhere in the middle, that happens as well. But the case in which it's different is if you have a 5 on the end. So if you have a 5 here. In this case, we can pick like a range of this size, but if we move this range over, it doesn't include this 5 anymore. It's only things that are bigger than the 5. So for this, if we have some ranges that look like this, all we're interested in is like the biggest range and then also the second biggest range, because we can't have the second biggest range be relevant. So it's got to be bigger than the second biggest range. It also has to be the biggest it can be is something that fits between these two ones, because otherwise we won't have any 5s. So those are the 2 constraints. What this means is we have a bunch of things like for each number, this was for numbers that are 5, but for every number, we'll have like some minimum. So we say it's got to be bigger than this number, and it's also got to be smaller than this number. And we want the intersection of all of those values. And that's going to be what our final answer is. Okay, so we also special case the permutation for 1, because that's different. Because like all of these observations where we can move the range over by 1 and it'll still include this element. Well, with ranges of size 1, you can't do that. Here's what the code looks like for that. My first D solution was just totally wrong. But yeah, okay, so I store the indices of every number. So I store like how many times each number occurs and where it occurs. And the first thing I do is, well, the thing I do at the end, I guess, is check if this is a permutation initially. So if every number occurs exactly once, then it's a permutation, which means it's possible to do size 0. So that's, I guess, a base case that we'll worry about at the end. But I do base case that out. I also have this tree set of all of the numbers smaller than the number I'm looking at, or all of the indices which have a number smaller than what I'm looking at. And I maintain this as I process all of the numbers. So, yeah. Okay. So then for each number, I maintain the tree set, but also I say what are this minimum and maximum, and then I store that as the bounds for this particular number. And then what I'm interested in is if the biggest number in my array is going to be like 7, for instance, then I need to satisfy the bounds for 7, 6, 5, 4, 3, 2, and 1, which means I need the constraints for everything from 0 to 7. I need those minimums to all be satisfied. So I need the maximum of those minimum requirements, and I need the minimum of the maximum requirements. Those all need to be satisfied. And those need to be in the range of the size of the group that I'm picking. So the size of the group I'm picking will uniquely determine what the biggest number in the permutation will be, or should be. That's just n minus I, and then I do minus 1 because I want my stuff 0 indexed, just for simplicity. But yeah, so that's the biggest thing in the permutation. The size will be I plus 1. That's how many things will be in this continuous window. And I check whether it's possible. Now this works, like I said, for everything except when the size is 1, and that's hard-coded. And I print all the answers at the end. Okay, yeah. Sorry, that was maybe a bit difficult to explain. I also just need to talk about how I calculate these maximums and minimums. So let me clean this up just a bit real quick. Boom, boom, boom. I think we should be good. Yeah, okay. So what I do is I get like a continuous range of 5s, like I mentioned earlier. I get all of the 5s between the first bound to the left of the 5, the bound to the right of the 5. And this is the left bound and the right bound. I get the first and the last 5. So now if there's only one 5, then the first and last will be the same. So this is checking if there's only one 5. And then this part here checks to see is the 5 at the beginning or end of the range. If it is, this is like the special case where I can have as many of these things as I want. Like the size can be as big as it wants, up to this size here. If it's not, the size has to be this size or it's impossible. This size or nothing. Okay. So I add all of the range sizes, and this is difficult to explain, I guess. But I add all of the range sizes, and this handles exactly the case that I was looking for. But it does it in kind of like a unpredictable way, but it ends up working if you go through all of the cases in your head. One thing I should mention here is if you have two, like if you've got like a 5 here with some 1s, and then you have another 5 here with some 1s, and these two ranges are the same size, then it's impossible, right? Because this range here, if it like fits in this range, it'll also fit in this range. So it's got to be bigger than the second biggest and smaller than the biggest. So the way I enforce that is I add a constraint saying, imagine there's some range of size, this size minus 1. We need to be either exactly equal to ourselves or it's impossible. And assuming we're the biggest one. So yeah, that's how that works. Okay, then the final answer is the second biggest one, if there is one, otherwise 1, up to, like 1 bigger than the second biggest one, excuse me, otherwise up to ourselves. So this is 1 bigger than the second biggest, and then this is the biggest range. Okay, that was messy explanation, but yeah, I don't know. I don't really know. Don't know how to do better. Okay, 2 problems left, and I got a few minutes to talk about them. Let's talk about, see if predictor caught me right when I was about to click. Problem F was the next easiest, probably, by a pretty large margin, I'd say. The strolling contestant, yeah. So in this problem, you're competing in a div 5 round. The one and only div 5. And you want to solve all of the problems in such a way that you solve the problems in almost like an adjacent order. So you might go from hardest to easiest, you might go from easiest to hardest. But you don't want to solve any 2 problems that are the same type in a row, because then you get bored. So you want to find what's the minimum number of times you need to like just jump to a different part of the contest in order for this to work. So yeah, let's look at one of these examples. The first example, the problem difficulties are 212, 311. So yeah, one way of doing this is you can solve this problem first, and then you can solve the rest of the problems in order. Then you solve every problem, and you had to jump once, so you had to make this jump here. Here's the observation. We know where we need to like imagine cutting this array up. We know almost all of that from the very beginning. So from the beginning, anytime you have 2 things in a row, you're going to have to cut the array here. And then we know like those cuts, but it's possible we might need to cut the array somewhere else later on. So they give us an example of what that might look like in the end. You have like 1, 2, 2, 1, 1, 2, 1, 2, 3, 1, excuse me. Then 1, 2, 3, 1. So you're gonna obviously have to cut the array here, but you can't join these 2 pieces together at all, which means you actually have to make another cut here that you don't want to make because you have too many 1s on your borders. And that's like the only other case that you have to watch out for. Now, it might be impossible. That's a pretty easy thing to watch out for. If over, like strictly greater than n divided by 2 ceiling If strictly greater than all of those are the same type of problem, that means even if you stagger that problem as often as possible, you still won't have enough room to put all of it. So this means that it's impossible. Yeah, the reason for that should be pretty self-explanatory, I think. Now, if it isn't impossible, that means you can do it. And here's like the thing to notice. So we've got, like, once we chop this array up, we've got a bunch of different parts. So we've got like this part here, maybe this part here, this part here, this part here. We've got all of these. Each of these have like two little like endpoints, right? We've got all of these endpoints. We have 8 of them. We need to hook up all but 2 of them. And we need to hook them up so that they're different. So if these 2 are different, we might want to hook those up. Maybe these 2 are different, so we hook these up. These 2 are different, so we hook these up. And now we have the start of our array here, the end of our array here. But wait, I hear you ask. This isn't one big chain like we need. Well, yeah, you're right. So we're not technically able to do this, but this is a good way of thinking about it. In this case, yeah, we've got this loop here. We've created this loop, and we're not supposed to have a loop. We're supposed to have one continuous chain. But the property of these parts right here is that they're different, right? So what we can do is we can like splice this up. We can cut this part in half here, and we can cut this here, and then we can join these together. So we can like join this like this, and then join this one like this. Now this isn't necessarily possible, but if it's not, then we can reverse these 2. So we can make this first one join this like that, and this join this. We know one of those will be possible because we know these 2 are different, right? So this is A and this is B. And then if the first one didn't work, that means this one needs to be an A, or this one's a B, right? These 2 aren't the same, which means we can flip them, and this isn't an A, so this is like not A, because we connected these in our first solution that had the loop, and then this one is an A, which means it's not a B. So yeah, there you go. So it's always possible to make some solution that follows like the real rules if we're able to find something where we connect everything. So we need to connect everything except 2 endpoints. That's the idea. Now, all we care about is the endpoints here, unless we have too many endpoints that are one particular type, in which case we're going to have to cut one of these things up. So the number of cuts we have to make is just the number of endpoints. So here we have this 8 minus 2 divided by 2. So that's how many endpoints we need. And then, or how many cuts we have to make in order to get all of these things. And then, oops, okay. Then we say, okay, how many like things that we have too many of will we be left over with? So let's say 5 of these are 1s. So we'll have a 1 here, 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 and here. That means these things in green are going to be not 1s. We don't know what they are. We don't really even care. But we'll match all of these up like this. And that's not right. This is also a not 1. Match these 2 up. And now we're left with some number of 1s. So if we're left with 2 or fewer 1s, then we can ignore them entirely, right? Otherwise, we, like for the number of 1s minus 2, every pair of those, we're going to have to create an additional cut for. So it's going to be the number of 1s minus the number of 0s minus 2, because we have the 2 endpoints, divided by 2. So this right here is going to be your answer. This first part is just like the number of cuts initially. So this is the final answer. And I'm pretty sure I just proved that that's right, but yeah, I don't know. That's my intended solution. It's possible that the authors had a more difficult solution because I don't think that was this hard, but I don't know, maybe. I saw it pretty quick at least. All right, last one, problem E, which I don't really have a solution to, but I'll explain my general path. The idea was you need, like, your graph needs to be bipartite. If it's not bipartite, you have an odd cycle, and that doesn't work because, like, if you add 1 here, then you add or subtract 1 here, and then you add or subtract 1 here, if you go along this path, you're going to change by an odd number. And you need to change by 0. Or I guess, yeah, you need to change by 0. So, like, that's not possible. So if there are ever any odd cycles, it's impossible. Otherwise, you know one of these things has to be the lowest. So we're going to brute force what that is. Let's say this is a 0. So now after doing that, we now have a bipartite graph. We know it's bipartite because half of the numbers will be an even height, half will be an odd height. Now we've got this bipartite graph. We're going to do a BFS from it. So let's do what we had in the sample, or something like what we had in the sample, which was this. Sorry, excuse me. Yeah. So we do a BFS from some node here. Let's say we BFS from this. This is distance 0, 1, 1, 2, 3, 3. We'll do this BFS. Then after we do this BFS, we are going to repeatedly need to pick some set of nodes and decrease its height. So this is the biggest the heights can possibly be. We need to make it smaller from here. And we can do this by like seeing some edge which is going in the wrong direction. Maybe this edge here needs to be, this one needs to be jealous of him. So this edge is going in the wrong direction. We start by picking this node here. We expand it as long as we need to. And then we decrease the height of everything in this set by 2. The only part that I have left is how do we know when we need to expand it? Well, if we have any edges that are forced to look like this, so maybe we have some node here where the edge has to look like this, which means this needs to be height 2 for whatever reason, right? We've previously determined it needs to be height 2. Then we need to keep this element smaller than this first element. So we'll expand it to include this node. The other case is if this node is jealous of someone like this. So if this is a 4, right? We need to make sure this doesn't become 3, that they don't differ by 3. So if even if this edge isn't forced, whether it's forced or not, we need to expand it here because this one is bigger than us and we have an edge toward it. So yeah, so we expand it like that. We keep expanding it. Once we haven't expanded it, we decrease everything by 2. If we ever expand it so that it includes this node here, then we won't satisfy this edge, which means it's impossible. And I think those are the only 2 impossible cases, but I'm not totally sure because I didn't solve it. So yeah, I thought it was a very fun set. Let's see, do we have scoreboard? Is our system test done yet? 77. We don't know yet. Okay, well, I have to go run a set, unfortunately. Well, I guess it's not unfortunate or not. I have to go do it. But that means I don't get to see whether I failed system test on one of these. If I did, it was more likely on C2, but it looks like my solution was probably right for that too. So it looks like I get to keep International Grandmaster, which I'm very excited about. It makes me very happy. And yeah, thank you for watching. I hope you enjoyed the set as well. Thanks to Monogon and friends, I guess the whole AC Discord, everyone who worked on it. Thank you guys for the fantastic set. I loved the flavor text on H1. I'll be thinking about it later for sure. Yeah, thank you for watching. And see you guys later. Hope you have a great day. Goodbye.